One of our jobs when we're talking about orbitals for electrons is to start with some visualization of orbitals. It helps us understand what's happening in the atom, and that's really going to help us when we start talking about bonding. So when we talk about the orbitals, remember we have four quantum numbers, n, l, m sub l, and m sub s. And this one is telling us about the energy, the principal quantum number. The angular momentum quantum number is telling us about the shape of the orbital. The magnetic quantum number is telling us about the orientation. And then this is specific to each electron. And we'll get more into that a little bit later. So when we're looking at our orbitals, we talk about the shell, that's the N, and the subshell, that's the L. And we know that our subshells, we have several. So we said that depending on the number, 1, 0, 1, 2, 3, 4, etc., we have S, P, D, F, and then some more that we mostly will not probably visualize. So when we talk about the shapes of the orbitals, all of these are coming from the Schrodinger equation. And I told you earlier that the Schrodinger equation is a mathematical function, and it's mostly represented in a two-dimensional graph, but it really has 3 dimensions. It has positive parts and negative parts. So you might have a mathematical function for the Schrodinger equation that is represented as being along the r-axis, so that's the distance from the origin, and you might see parts of it and it might look something like this, just for an example. So we have a 2D representation, but they really have 3 dimensions in here, and so usually we will try to do some 3D visualization as well. The other thing to know about the orbital, this is the equation of the orbital that describes what's happening with the electron and where it is. And since we actually not want to know statistically where it is, most of the time we are looking at what is effectively the square of the function, because we just want to get an idea of which are the high parts. So when we square the function, all the negative parts become positive, and then the amplitude ends up getting increased as well. And so you would convert this mathematical function into something like this. And this is what we call a probability density. It's a fancy name, but what we're really just talking about is where are we most likely to find the electron? Since this is a graph in r, the distance from the origin, the places where you are likely to find the electron are places with high values on this psi star psi axis. This is a probability axis. So we are most likely to find the electron here, and then if that doesn't work, here's our second most likely location. Okay, so really we have 2 main places where we have a very high probability of finding an electron. Remember, electrons are not like macroscopic objects, and so we have different ways of describing what's happening with them. All right, so let's go ahead and take a look at some visualizations. What we're looking at here is figure 723 from our textbook. So up here, this is a description of what the electron density looks like if you just square that function. But rather than just squaring it, we've also changed it so that we are scaling it for a circle. And so this will give us that psi star psi function, or the psi squared, and then 4 pi r squared gets us this cross-sectional area for a circle. And so this is what we are going to be sort of imagining for our probability function here. But what you can see is that really what happens is that closest to the origin, this is an s orbital, closest to the origin is where you are likely to find the electron. Of course, you won't actually find it at the origin because the electron isn't going to be on top of the nucleus. But instead, we're going to find it, somewhere close to the nucleus. Anyhow, we have several different representations here, so let's take our time looking at them. This first one is that straight ahead square of the mathematical Schrodinger equation. And this one is the slightly modified version that I mentioned. The reason why we do this spherical thing is because this really is a three-dimensional function here, and it is the shape of a sphere. It's not just a two-dimensional function. The other two representations here, these are on the left-hand side. This is called a density dot diagram, or at least that's one of the ways of talking about it. And what we have is we have a bunch of little dots showing where the highest areas of density are. And then notice this mathematical function never actually stops. We just stop drawing it. But it really goes out to infinity. We can't draw out to infinity though, so we choose to stop at a specific place. So usually it's at the 90%. So we contain 90%, or sometimes it's 95% or 98% of the density that's underneath this probability function, that we have 90% of the area represented by this radius r. This one on the right-hand side is intended to show it in 3 dimensions. So this r right here would be the same as that r right there, so whatever that radius is. And you can see that this is superimposed in 3 dimensions, also over the top of the x, y, and z axes. Right? So this is what that s orbital looks like. Specifically, this is a 1s orbital. So let's take a look at our next simplest orbital, which is our 2s and our 3s orbitals. And we have some pictures here in the book too, so let's go ahead and take a look at them. So this one on the left, this is, we have our two things here, right? We have that modified Schrodinger equation. This is our 1s orbital, and they have a cutaway showing us the density dot overlaid on this sort of cutaway of a sphere. So this is giving us the idea that at the origin we have our highest concentration of where that electron is likely to be. Also take a look at the actual distance from the nucleus. This is in picometers, and it looks like we're around 100 picometers from the nucleus for this atom. It's probably hydrogen. This is the most common element that tends to get graphed here. So here's the 2s orbital. It's still spherical, as you can see from the cutaway, but it actually has a little place here where the function equals 0. That's called a node. And it has 2 regions of density. This one close to the origin doesn't have as a very high peak here, and that tells us that the most likely place for our electron is probably over here at around 300 picometers, so a little further from the nucleus. So this electron that happens to be in the 2s orbital is going to be further from the nucleus than if it were in the 1s orbital. It would probably most likely be hanging out right around here at 100 picometers, and then if it moves up to the 2s, then its most likely location is around 300 picometers. Now over here we have a 3s orbital, which is also the same. It's spherical, but rather than 1 node, it has 2 nodes. And so the 2 nodes here are also places, all of these nodes. Nodes are places where the electron will never be found. The function is equal to 0, and the probability is equal to 0. So you can see on this 3s orbital that we have the most likely location is out here at around 700 picometers for where that electron is most likely to be found. So remember that we said that those s orbitals only have one orientation. This is because they are spherically symmetric. They look identical in 3 dimensions. There are no separate sides to them. So let's take a second and review what we know about our p orbitals now. So our p orbitals, we know that these can start with an n is equal to 2 because we need to have an L equal 1. So when we look at the other quantum numbers here for the p orbitals, if we have a 2p orbital, that's n equals 2, L equals 1, then our m sub L values are equal to -1, 0, and +1. And this is actually true for all p orbitals. They will always have these 3 m sub L values, which we said means that we have 3 orientations. And I also mentioned that we name these 2px, 2py, and 2pz. And the reason for these is how we represent them on the Cartesian axes. This is figure 7.25 from our book, and we have the 3 p-axes, 2px, 2py, and 2pz, and then over here all 3 of them superimposed on each other. So take a look at where the 2px orbital is, and where the 2py orbital is, and where the 2pz orbital. So you can pretty clearly see that the little label on these is because we have oriented them with the x, the y, and the z axes going straight through the areas of density for this orbital. Okay, so we have these 3 different orbitals, and as you can see, these areas where we have a bulge, and this is intended to show where our areas of density are. So the most likely locations for this electron in the 2px orbital would be somewhere in the middle of this bulge. And the same thing would be true for the 2py and the 2pz. Now, how can they be having the same probability in both places? We don't really understand that, and that's just because they are quantum mechanical particles. They do not behave like macroscopic things. So remember, this is part of their wave-like characteristics. It doesn't need to be relatable because most quantum mechanical things are not relatable. We don't experience anything that has these kinds of properties. So it's okay. Don't worry about it. All right, so those are the p orbitals. And just like with the 1s, 2s, and 3s orbitals that we saw, we can have p orbitals that have higher n numbers too. So if our 2p orbital had these 2 lobes, we typically will draw them with a different shading on one side versus the other. And so this is my little orbital sketch. And this is because in the mathematical function, this mathematical function would have looked something like this. So that when we square it, we now have 2 areas of density that match up with our 2 little lobes, and we've just cut them off at the 90% surface, just like we did with the p or with the s orbitals. But the reason why we shade them is to acknowledge that these 2 halves had different signs initially, and so we want to be able to remember that these 2 parts of the orbital are not identical to each other and that there is a node in between them. And we've now seen 2 kinds of nodes, so that's how many nodes we have, or types of nodes that we have. So let's take just a moment and talk about nodes. Our 2 types of nodes are radial nodes, and they happen at a specific radius, but not at the origin. Then we have angular nodes, and these go through the origin. And we're going to learn more about how to tell the difference between our radial nodes and our angular nodes pretty soon. So if we look at these two nodes, this one we would draw as kind of a plane in between here. That we can see that this would extend all along. If I had my axis, my additional axis coming out of the paper here, then all along this, it's probably what? If this is my x, then this would be my y, and this would be my z. So this node would be right along that YZ plane, in between the two lobes of my orbital. Now, on the other hand, let's just sketch what we had for that 2s orbital just a minute ago. Remember how we had this sphere? Well, it also had a cutaway, right? And there was this region in between. So if we drew that as a two-dimensional thing, we had a little part toward the origin, and then we had a bigger part, right? So this is at a specific radius. And this is where the node is. So this would be an example of a radial node because it's at a specific radius that is not equal to the, or that is not at the origin. And this would be an example of an angular node. And the angle at this point would be like 0. So, but we'll get into more about these angular nodes, as I said, in a little while. But I just wanted to point out those two different kinds. We can start recognizing them. All right, so our third type of orbital are going to be the d orbitals. And we know that n is equal to 3 is the smallest number where we can have d orbitals because we need L is equal to 2. So these would be 3d orbitals. And then m sub L, we would be having -2, -1, 0, +1, and +2. So we have 5 orientations. So let's take a look at them. All right, this is figure 7.26 from the book. And the numbers are a little, or excuse me, the letters are a little bit small in the video, so I will mention the labels here for you and then draw them for you. So just like before with the p orbitals, we have designations for each of the 5d orbitals. So this is a 3d xy. Notice that the x and the y axes are actually in between the lobes of this orbital. Then we have a 3d xz, where that's the same thing. The xz lobes are all along the plane of xz, but they are in between the axes. Same thing is true for this 3d yz, so it's the same deal for all three of these orbitals. They're just perpendicular to each other. And then we have the 3d x squared minus y squared, where these ones are actually on the axes instead of in between all of the axes like those other three. So I always think of this one as slightly different from these other three because it is oriented on the axes rather than in between the axes. And then we have this funny one that's called 3d z squared, which always kind of looks like a donut with two ice cream cones. And that's how I remember what its shape is. So this is sort of the weirdo in terms of what kind of shape. Well, it's not the weirdo, it's just the unusual one where all the other ones have a very similar shape, and this one has a different one. Now, why are these the shapes that they are? This is a complicated answer, and it comes down to lots of math, and we aren't going to go into it. If you are excited about math and you want to learn more, I would be happy to talk to you about it outside of class. So let's take a second and draw these orbitals. Now typically, because I'm not very good at drawing in 3 dimensions, I'm just going to draw mostly 2-dimensionally. And I'm just going to be careful with my labels. So I know that my 3D XY labels are going to be in between the X and the Y planes. Now, just like with the P orbitals, we also have a different sign for half of our orbitals. So notice that these ones are opposite each other, and also these are going to have nodes in between too. So these ones also have 2 angular nodes. And this is true for all of the d orbitals. They have 2 angular nodes each. So this is the 3D XY. And then my other ones are going to look exactly the same, except I'm just going to change the labels. So these are 3D XZ. And then my last one is YZ. So this is 3D YZ. Okay, and now the two that are slightly different. So this one was X and Y, and they're on the axes. And just like before, we're going to have 2 different signs. It does not really matter which 2 you shade in, as long as they're opposite from each other. So these ones are the x squared minus y squared. And then our last one is the donut plus ice cream cone. So I'm going to draw my little donut here, and then I'm going to draw my ice cream cones as well as I can. And this time the shading is going to be the donut is one shade and the ice cream cones are the other shade. And this was the 3D z squared orbital. All right, so this gives us a basic idea of the shapes of these orbitals. And we should be able to draw and recognize each of these orbitals. You should also be able to remember what our orbital designations are for the 2p and the 3d orbitals. I will not ask you about them for any of the other orbitals, but for these 8 orbitals, you should be able to probably draw where they are with the appropriate axis labels and names.